Chapter 2, Functional Groups. Part 1 is what is a functional group, and also we're going to cover alkanes. So this topic list is a rundown of the entire chapter. We're going to start with an introduction to functional groups. That includes hydrocarbons, alkyl halides, alcohols, ethers, amines, aldehydes and ketones, carboxylic acids, esters, and amides, nitriles, and then we're going to look at physical properties of organic compounds, including a review of intermolecular forces, solubility of organic compounds, and then briefly we'll touch on IR spectroscopy. So let's take a look at functional groups. Functional groups are the part of the molecule that undergoes reactions. So what you'll start to notice as you get further into organic chemistry is that most molecules have a lot of carbons that are essentially inert. They are not part of any of the organic reactions that we're studying. Instead, there is a small part of the molecule or several pieces of the molecule that are functional groups, and they are the actual parts that are going to do chemistry. The technical definition is a common and specific arrangement of atoms that imparts a predictable reactivity and properties to a molecule. In other words, all carboxylic acids undergo the same reactions. Amines will undergo a different set of reactions. Alcohols react in a certain way. Ethers react in a certain way. So if you can group reactions together based on the functional group, then organic chemistry becomes a lot simpler. Rather than trying to look at individual molecules, focus on the functional groups themselves. You're not going to hear me say to memorize a lot in organic chemistry, but functional groups and their structures are things that you can memorize. So I would make flashcards of them. Basically right now, make flashcards and just start using them whenever you have a couple spare minutes, and learn to recognize the patterns both within the molecule and then within reactions as we get into reactions. So let's start with hydrocarbons. Hydrocarbons aren't exactly a functional group. They're not particularly reactive exactly, but it is a large piece of molecule. Hydrocarbons are a wide class of compounds containing only carbon and hydrogen. And they can be broken down. So I have this kind of flow chart here to break it down into categories. So the simplest of the hydrocarbons are the alkanes. We'll cover them in Chapter 4. Alkenes are going to be covered in Chapters 7 and 8. Alkynes are covered in Chapters 7 and 8. And aromatic compounds are covered in Chapter 14. Now, this doesn't mean that the hydrocarbons have nothing else on them, because what you'll learn is that when there are no functional groups present on hydrocarbons, they tend to not do a whole lot. But when you start to add on different functional groups, they can do a lot of chemistry. So alkanes are only single bonds. Alkenes have at least one double bond between carbons. Alkynes will have at least one triple bond between carbons. And aromatic compounds follow a totally different set of rules. So aromatic compounds are not covered until you get to organic 2. So we're just going to kind of block that off for now. When you're naming an alkane, it uses the ane suffix. So for example, CH4 is called methane. The meth prefix says there's one carbon, and the ane suffix tells us that there are no multiple bonds between carbons. Other examples include butane. This is a 4-carbon alkane, and don't get hung up on naming right now. Naming is Chapter 4. This is cyclohexane. So notice I'm just using the ane suffix, and there are no double bonds present in these molecules. And then on this molecule, we have 3-ethyl, 2-methyl pentane. Alkenes use the ene suffix, ene. So notice that these suffixes match the names of the hydrocarbon class. So for example, a 2-carbon molecule that has a double bond, so the actual structure of this looks like this, would be called ethene. Eth is the prefix for 2 carbons. So here are some examples of various alkenes. Alkynes use the YNE suffix. So for example, a 2-carbon alkyne, which means there's a triple bond between the carbons, is called ethyne. An interesting thing about alkynes is that the geometry between a triple bond is linear, and so also the other pieces that are attached to those carbons are going to be linear. And if those other pieces are carbons, you actually have these 4 atoms that are all linear. So there is a carbon here, a carbon here, carbon here, and carbon here, and they are all linear. And then aromatic naming is quite a bit more crazy than that. So for example, we have C6H6, which is benzene. Benzene is here. This compound is called naphthalene. Now there's one more kind of breakdown of hydrocarbons. Alkanes are known as saturated hydrocarbons, and we'll get to what saturated and unsaturated means in way more detail later. But for now, what you want to know is that saturated means there are no multiple bonds present. So everything that we're looking at are single bonds between carbons. So every carbon has the maximum number of bonds to hydrogen possible. And anything that has a multiple bond is going to be unsaturated. Now there is kind of a caveat here. Forming a ring is actually a type of unsaturation, so cyclohexane doesn't quite fit in there. So saturated versus unsaturated hydrocarbons, a little more detail. Saturated hydrocarbons have the most possible number of bonds to hydrogen atoms. So for example, you can calculate the number of hydrogen atoms that should be in a molecule if it was fully saturated by taking the number of carbon atoms and multiplying by 2 and adding 2. So for example, the formula of pentane, which is just 5 carbons, is C5H12. And we can actually calculate the number of hydrogens by taking the number of carbons, multiplying times 2, and then adding 2. And these numbers don't come from nowhere. If we take a look at all the carbons on here, all of the inner carbons have 2 hydrogens on them. All of the terminal carbons, the ones at the end, have 3 total, but here are 2 of them. So if we multiplied 5 times 2, this would give us 10. And then since these are terminal carbons and they do not have any more bonds to other carbons, they also have to have 1 more hydrogen. And that's actually where the plus 2 comes from. It's these guys right here. So this part of the calculation gives you the orange hydrogens, and then that plus 2 gives you those like capping hydrogens. So that's where that's actually coming from. Unsaturated hydrocarbons have less hydrogen, and you can do this with multiple bonds or with ring formation. So the number of hydrogen atoms in an unsaturated hydrocarbon is going to be less than 2 times the number of carbon atoms plus 2. So for example, pentene, there are actually multiple forms of pentene, but let's just pretend that we're using 1 pentene, is C5H10. So if we go through and put all of these hydrogens on here, there's only going to be 1 here. This is actually going to give us 10 hydrogens. And that's because this multiple bond here took away the spots of 2 hydrogens. So there are 10 hydrogens total in the structure. Oh, hey, look, another molecule. There's also cyclopentane, which I guess I must have drawn here as well. There it is. Cyclopentane does not have any multiple bonds, but because the ring is connected, there are only 2 hydrogens on each carbon. So the end capping hydrogens that we were looking at up here their spot is taken by this bond between the 2 carbons. And then we can also look at pentyne. So pentyne, everything over here is the same as what we've been seeing, but this carbon here has no hydrogens on it, and this terminal carbon only has 1 hydrogen. So we have 3 here, 2 here, 2 here, and that gives us 7 plus 1 on the end is 8. And then you can also have something like cyclopentene, which has a double bond within the ring, and that's going to take away another degree of unsaturation. So let's take a look at alkanes. There are some prefixes that you can start to memorize now. Methane is CH4, ethane is C2H6, propane is C3H8, butane is C4H10. Something that you could start to memorize now that will come in handy later is that meth means that there is 1 carbon in the compound. Eth means 2 carbons. Prop means 3 carbons, and but means 4. So let's look at these molecules. Methane is going to be a tetrahedral molecule with 1 carbon and 4 hydrogens. Ethane has a single bond between those 2 carbons, and both of these carbons are also tetrahedral if you actually draw it out. Now, the line bond form for ethane would just be a single line, which is why ethane is typically written out instead, is because this single line could be anything. It could be, a misplaced dash or something. So you usually don't start doing the line bond structures until you have propane at least. And there is no line bond form for methane because it would just be like a dot or something, so not very useful. Now, alkanes with 1 to 4 carbons are gases under ambient conditions, so regular pressure, regular temperature. Methane, ethane, propane, and butane are gases. When you have 5 to 16 carbons in an alkane, they tend to be liquid, and 17 plus are going to be waxy solids. Methane is the principal component of natural gas. And alkanes C5 and up are mostly obtained from petroleum refining. Also, these bigger carbon-containing compounds are the components of gasoline. They are highly combustible. There's actually a lot of stored energy in carbon-carbon and carbon-hydrogen bonds. Let's take a look at alkenes. This is just some fun facts about these different compound classes. So ethene is also called ethylene gas. This is a common name for it, whereas ethene is the official IUPAC name, and we'll talk about IUPAC a lot in chapter 4. Ethene is the simplest possible alkene because you have to, since it's a double bond between carbons, you have to have at least 2 carbons. And it is produced by plants during the ripening process, which is where you usually hear the word ethylene gas being used. Ethene and propene. Propylene is the common name for propylene or for propene. They are really important in the chemical industry. About 30 billion pounds of ethene and 15 billion pounds of propene are produced annually. And that's because they are building blocks of polymers that are used everywhere. So polyethylene and polypropylene, and many other important organic compounds. You can do a lot with just a small alkene. Many alkenes are also naturally occurring. So some more complex alkenes. This compound here is actually featuring 2 different alkenes. And then notice also that we have some directionality being shown here. We haven't talked about stereochemistry yet. That's chapter 5. So we'll talk about why that dashed wedge is important in chapter 5. This is limonene. This is a naturally occurring alkene. It's going to be oily, and as the name suggests, it is one of the common compounds found in like a lemon oil. So if you have lemon essential oils or something like that at home, limonene is in there. And this compound is humulene. It's fairly complex. I mean, look at all these many carbons, and you have kind of a large ring here and 3 alkenes. This is a component of the essential oil that is derived from hops. So this is one of the flavor components of like a hoppy beer. Okay, so another thing that you'll see a lot in organic chemistry is the use of the symbol R. And R is usually used as a generic symbol to represent any alkyl group. It's a placeholder used for carbons when we're trying to focus on a functional group. And the reason I'm showing you this is because we're about to learn different functional groups. And so we're going to use the letter R a lot in order to just take the place of the carbons so that we can focus on the functional group. So for example, if you look down here at the bottom, the general formula of an alkane is RH. And what that means is that this is any number of carbons and hydrogens, but there has to be a hydrogen on the end of that link. So let's look back up here at the top now. If we looked at methane, we could isolate that 1 hydrogen on the end there. And if you remove that hydrogen, this becomes a fragment of a molecule, which is called a substituent. And that makes it an alkyl group, something that can be substituted onto a larger molecule. So for example, you can have propane, and on the second carbon, we can add on another CH3 group. That would be a methyl substituent, and we would end up calling this 2-methylpropane. The structure of a methyl group is H3C. And if you're looking at the bond line form, this wiggly line here means that it's attached to something larger. We can also use the abbreviation Me for methyl. You can do the same thing with ethane, propane, and butane, where if you take off that terminal hydrogen, they become molecule fragments. So they are called ethyl, propyl, and butyl, and they all have their shorthands as well. So our last substituents that we need to learn before we move on to functional groups are phenyl and benzoyl substituents. So phenyl and benzoyl are both substituents that contain a benzene ring, but they are connected by a different number of carbons. So when you have the phenyl alkyl group, it is attached directly to something else. So for example, if we have a 7-carbon chain and a benzene is directly attached to carbon number 2, this would be called 2-phenylheptane. If we have that same 7-carbon chain, let's put the benzoyl ring right in the middle, then this would be called 4-benzylheptane. And the reason that phenyl and benzoyl are different is because of this. That is a CH2 group separating the benzene from the rest of the molecule. So we have our heptane, we have CH2, and then we have benzene. So that's the difference between benzoyl and phenyl. Notice that phenyl is directly attached to the alkane. There is no CH2 group in between.